So hello guys, this is the second application video of Ebbinghaus techniques for revision. So in this video I will revise what I already studied, that means the day before yesterday and yesterday's studies. So let's see. So what I already studied day before yesterday, let's see. So I studied what is fluid. I will shortly revise. So what is fluid? Fluids are three types: solid, liquid and gas. Liquid and gas are known as fluid, and fluid can flow. Flow means deformation, plastic deformation. Okay, that means permanently shape change. Fluid can flow. Flow means permanently change. That means continue plastic deformation happen. Okay, so in this is very important thing. And then I already studied fluid is a substance. Fluid is a substance that deform continuously under the action of shear stress, however small shear stress may be. It may be small stress, shear stress. That shear stress can affect the action of deformation of fluid. Okay, so and once again I will say that I will say, so fluid is a substance that deform continuously under the action of shear stress. So continuously it deform under the action of shear stress. Okay, what I already studied. Fluid cannot resist shear stress. Fluid cannot resist shear stress. Remember that. Under static condition, fluid cannot resist shear stress under static condition, but it can be resist. However, it can resist shear stress under dynamic condition. It is, remember. Okay. So we are like in sum, we are small change. We are defining that time shear strength. But in this fluid, we are defining the rate of shear strain. No, there is not any terms like shear strain only in fluid mechanics. It is valid only for some. For fluid mechanics, it is valid only for rate of shear strain. Okay, which is d alpha by dt. And then I already discussed finite process, continuous process, finite amount or continuous rate. Something is happening, that means rate that we consider, or scientists are considered as a rate. Okay, then in fluid it is very important. In fluid, rate of deformation is more important than deformation. Okay, because fluid continuously deform as long as external force is there. Okay, then I have external forces three types: tensile, compressive, shear. Okay, see, we are studying now in shear according to the definition. We are studying now shear. Shear stress is the cause of change of or deformation of fluid. Okay, some characteristics I already discussed, like response to shear. What are the behavior of these characteristics by solid, liquid or gas? Let's see. Characteristics. One character first is respond to shear stress. Resist total deformation. Liquid resist rate of deformation. Okay, liquid and gas also both only resist total deformation, resist by some amount of the solid, but liquid or gas resist rate of deformation, and it will resist only in static condition, not dynamic condition. In dynamic condition, but static condition it cannot resist. Okay, it is a very important thing to remember. Then compressibility. As so respond to shear stress. So as liquid gas have also ability in dynamic condition that it can resist shear stress. So definition as include in this type. But in static, which we are now read, this is for static condition, which in which fluid, that means liquid or gas cannot resist the shear stress. Okay. Then compressibility, another character, incompressible for solid, and liquid for incompressible, and gas it is for compressible. Okay, gas can be compressible, liquid incompressible, but liquid also compressible, but little bit incompressible, so we are including in the category of incompressible, and solid also incompressible. But incompressible also for liquid. Okay, so we will discuss on this topic compressibility now, later, or 5 minutes later. Ability to deform, another characteristics. Ability to form free surface. Solid, yes. Liquid, yes. Gas is no. Gas is no ability to form free surface. Okay, that time I already said that if there is a nitrogen or oxygen, if there is, we remove boundary between them, they can mix with each other. They cannot form any free surface between them. Okay. So gas has no ability to form free surface. The another characteristics is ability to expand without limit. So in solid no, liquid no, gas is yes. Okay, that means which I already explained, that means ability to expand without limit. That consider these are two ball, and these are two solid ball. They have a cohesive force, as they have very large amount of cohesive force between two solid, so they cannot expand without limit. That means it can expand within a limit. That means expand, that means not broke, we are not considered broke type of thing. No, we are considering that it will expand. That means it has a limit. The ability to expand without limit it has only in gas. Okay, so another category is ability to conform shape of the container. Okay, so in this also solid no, obviously, liquid gases. And another ability to resist small amount of tensile stress. Some amount of tensile resist will by only by solid. Liquid no, liquid yes, yeah, some amount also liquid yes, theoretically some amount, and gas has no. Okay, now I am discussing of what I already studied yesterday. Okay, let's revise, and let's see. First concept is concept of continuum. So what is concept of continuum? So simply one line, if I say continuous distribution of matter is known as concept of continuum. That means hypothetical matter without void. That means if there is a pen, if a solid body, there is an infinite number of molecules are there. So but concept of continuum is saying that between these solid there is no void, but actually it is not practical. If there is very small amount, mostly voids are there, but as concept of continuous saying that continuous distribution of matter, that means there is no void in between matter. It is very it is only theoretical but not practical. Okay, so yeah, another line, if continuous fails. So why we consider that? And it is considered because we need a physical system. We try to prepare mathematical model of it. So there is no any mathematical model that some point is void, some point is continuous, some point is void. There is no any mathematical model to explain in thoroughly. So we have to be considered that there is no void in between matter. So that we are thinking that it is totally packed and there is no void. So we can apply the concept of mathematical model. As we have no any type of mathematical model with us, so we have considered that there is no void in between matter. It is the main reason. So let's see another 2 point. So If so, due to that we are introducing concept of continuum. Okay, if someone asks, if continuous fail, what will happen? If continuous fail, we cannot write fluid properties as a continuous function of space variable. We cannot write mathematical model. You can see. So we cannot write fluid properties. If concept of continuum fails, we cannot write fluid properties as a continuous function of space variable. It is a space, that means 3-dimensional variables from there. So we cannot write that thing. Fluid properties as a continuous function of space variable. We cannot write fluid properties as a continuous function of space variable. So we have to be considered. So for the explanation of fluid properties, we have to be right, or we have to be consider the concept of continuum. Okay, but how long it may be, but it may somewhere fails also. So where it fails? So in rarefied gas flow, where gas with a very low density, that time continuum fails. Where for example flight or rocket in upper atmosphere, there is very low density. So there, if I apply continuum, or if I observe continuum, concept of continuum will fail. And another thing is very higher order of vacuum. Where very higher order of vacuum is there also concept of continuum also fails. Okay. Another number, that is Knudsen number. So Knudsen number is lambda by L. Lambda is mean free path and L is characteristic dimension. Okay, let's see what is the significance of Knudsen number. Okay, discuss. So as we know, the formula of Knudsen number is lambda by L. Okay, so what it define that mean free path. Okay, so in mean free path, distance traveled by gas molecule between two successive collision is mean free path. That means there is many type of molecules are there. Okay, there is one molecule, there is one molecule, there is one molecule. It's different types of molecule in the continuum. There is a point, there is a molecule is there. Let's see. There is a molecule there. There is also a molecule. When it attracts each other by cohesive force, they will collide each other. Some molecule will reflect, or we can say diverse in this direction. But in this place also some molecule are also there. So that time also one molecule also collide with each other. So this point and this point, where same molecule are collide, dash distance is known as mean free path. Okay, so it is the very important thing. And so it will show Knudsen number is lambda by L, and lambda is mean free path, and L is characteristic dimension. Okay, so as I mentioned, or as I described, that distance traveled by gas molecule in between two successive collision is known as lambda. Okay, and this is known as Knudsen number, which is lambda by L. L is characteristic dimension. Okay, L is some characteristic dimension. Okay, so I already demonstrate how by to cap. Okay, remember one thing: if mean free path is more, then density of gas is less. Okay, if mean free path is more, then density of, that means lambda is more, then density of gas is less. Okay, remember this Knudsen number has should be less than 0.01. Okay. So Knudsen number is just assumption. We need try to prepare mathematical model. We want a mathematical model so that we need some number, some definite numbers. So Knudsen number is a example that how we can make a model. So without this we are not going ahead to make any type of mathematical model. So it will help to build a proper mathematical model for in fluid and many other subject also. Okay, many things, actually many things what we are studied in our earlier classes, all are many things are assumption. But if you think of, if you look in that in this thing on the practical life, it will very different thing. Okay, so due to assumption we can define something easily. So we are defining or we are assume many things. Okay, let's see next, go ahead. One thing we should remember, if mean path, that means distance between collision, mean path, free path, that means distance between two collision is high, then given space number of molecular less. If free path is high, that means you have to go a larger distance, so that for that another collision. So that time we can say there is molecule number is less. If molecule number is more, then the successive collision, distance of successive collision will be less. Okay, this should be remembered. Okay, then properties of fluid. Now we are entering the properties of fluid. First property, density. Density is equal to mass per volume, and the what is its unit? Unit is mass is kg in SI unit, and volume is meter cube. So unit will be mass per, kg per meter cube. Okay. If you see in CGS system, it will be gram per cubic centimeter. Okay. So you have to be, if we will write in CGS system, we have to be convert SI system into CGS, so that we can write this in CGS. So in CGS, if I write 1 gram per cubic centimeter, that means in SI 1 kg per meter cube, that will be in CGS 1 gram per cc, that means 1 gram per cubic centimeter is equal to 10 to the power minus 3 kg by 10 to the power minus 6 meter cube. That means 1 gram is equal to 10 to the power minus 3 kg divided by 10 to the power minus 6 meter cube. So you can say 1000 kg per meter cube. That means 1 g by cc. That means 1 gram per cubic centimeter is equal to 1000 kg per meter cube. It should be remembered. The value should be remembered. 1 gram per centimeter cube is equal to 1000 kg per meter cube. Okay, well, remember one thing. If you look at the thing properly, you will say that this is kg and this is gram. So what I said, that the formula is 1 gram per centimeter cube is equal to 10 to the minus 3 kg by 10 to the minus 6, which is 1000 kg per meter cube. So you will say no, kg is large, that means gram unit is less, that means kg unit is large. No. In this, if you look properly, 1 gram per cc is 1000 kg per meter cube. So if you just look at in view of the number which is associated with this unit, then you can observe the 1 gram per cubic centimeter is 1000 kg per meter. That means here 1 gram, that means here gram value is large, bigger than the kg per meter cube value. That means 1 gram per cc is equal to 1000 kg per meter cube. That means 1 kg per is less unit according to the unit. That means according to the value, if you observe, then 1 gram of cubic cubic centimeter is bigger than the unit of 1 kg 1000 kg per meter cube. Okay, let's see. So if you compare liquid to gas, this density property with this density property, if you compare these two things, liquid and gas, so you will see that density of liquid is more greater than density of gas, obviously, because if you look at liquid molecule, it is more compact than gas. So the gas has, we know there is no limit, expand limit is less, so it can expand without its limits. So obviously the density of liquid is greater than density of gas. Okay, so standardly we are assumed that or we are verified that, we are calculated that density of water is 1000 kg per meter cube. Okay, for gas also it can be 1 kg per meter cube. That means we are now comparing liquid and gas. So for gas, for liquid, I tell that one liquid is water. So for that 1000 kg per meter cube is 1000 kg per meter cube is its density, so that it will greater than gas. No. It can also be the density of air or the density of gas may be 1000 kg per meter cube, but pressure should be very high. So what I want to say that at the same pressure and temperature, in particular pressure and particular temperature, the density of a liquid is more greater than density of gas. Okay, so if we increase the pressure, the gas density also increases to 1000 kg per meter cube, obviously. So in particular pressure and temperature, fixed particular pressure and temperature, the density of water or density of liquid is greater than density of gas. Okay, then another property, specific volume. Specific volume is just the opposite of density. We know density is mass per volume, so specific volume is volume per mass. So obviously the unit will be meter cube per kg, or you can and if you write this unit, so meter cube per kg, and its formula will be 1 by density, or which can be volume per mass, or 1 by density. Okay, density, the reverse of density. Okay, then another property, specific weight. Specific weight is denoted by lambda. So lambda will be weight by volume. Density is mass per volume. Specific weight is weight by volume. Just G will be multiplied. Mass into gravity, that means G divided by volume. So the unit will be mass is kg, gravity will be meter per second square. So and volume is meter cube. So overall the formula of specific weight is equal to mg by v. M by v is common and g will be further. The m by v is rho g. That means m by v is density. So we can write specific weight in terms of density also. So we can write density, that means rho g. Okay, so the unit will be, we can know the unit of density, which is mass by volume, that means kg per meter cube, and into multiply with g is meter per second square. So you will get Newton per meter cube. It is the unit of specific weight. So specific weight is rho g, which unit is Newton per meter cube. Okay. It should be remembered that means at any type of objective type question at the same time or at that instant we can apply the formula directly and we will get the answer very quick manner. So we have to be very focused on that and we have to be remembered by day. Okay, it will help in your examination future, and if you remember that particular thing, it will benefit in also higher study also. Okay, let's see. Then another property is specific gravity. Specific gravity is density of fluid, that means density of any fluid divided by density of standard fluid. Okay. What specific gravity? So density of any fluid, that means it may be oil, it may be kerosene, it may be diesel, maybe phenyl, maybe anything. So density of any fluid divided by density of standard fluid. So now one thing is, what is standard fluid? So we can say standard fluid may be two types. Standard fluid means liquid and gas. So standard for liquid one, standard for gas one. Okay. So for standard liquid we are assuming water, and which has density we already know 1000 kg per meter. But if we practically observe or practically demonstrate, then we will see that at 1 atmospheric pressure and 20 degrees Celsius, the density of water is 998 kg per meter. That means 998 kg per meter, but we are assuming as 1000 kg per meter. So for simplify calculation, okay, like that. For gas has also a standard fluid. So for gas we are considering standard as air or hydrogen. So I am now telling about density of air. So we are considering density of air is 1.2 kg per meter cube at 1 atm, that means 1 atmospheric pressure and 20 degrees Celsius. That means pressure and temperature fixed. I already told that. Okay. So at that time density will be 1.2 kg per meter cube. At that same pressure or at that same temperature, constant temperature pressure, the density of liquid is 1000, that means 998 kg per meter cube. We are approximately 1000 kg per meter cube. So you can observe that how density of liquid is large than density of air. So at that same temperature pressure, that means 1 atmospheric pressure and to 20 degrees Celsius, the density of water is 998 kg per meter cube, which is 1000 kg per meter cube, and for air it is 1.2, only 1.2 kg per meter cube. Okay, so it will be the matter. And one thing that many students have doubt, that what do you mean actually by space? It is that formula, okay, the density of fluid by density of standard fluid is equal to specific gravity. Actually we are defining or we are using specific gravity for which fluid is heavier than water. That means which fluid is heavier than, how much heavier than water. For this reason we are calculating or we are concerning our specific gravity. For example, if we see Mercury's specific gravity is 13.6. That means Mercury is 13.6 heavier than water. That means 13.6 heavier than water. It is only the basic meaning of specific gravity. Okay. Next we are discussing about compressibility. Okay. This compressibility concept is very important for all examination, all science program, and all kind of conceptual subject. Okay, So compressibility, what is? So compressibility we are defining, and first of all it is denoted as beta. So as per its definition, compressibility is the ratio of volumetric strain to the change in pressure. That means volumetric strain divided by change in pressure. So volumetric strain what is? dV by V. That means change in volume by original volume. That is volumetric strain. And change in pressure divided by change in pressure. That means dV by V. That means whole together, if I will say, to whole together dV by V divided by dP is equal to volumetric strain, and in this one minus sign will be included. So minus dV by V divided by dP. So we will discuss on this for more time because it's a very conceptual thing. So if we see that compressibility also written as minus 1 by V into dV by dP for only rearrange this thing, and it will be may be defined as d rho by rho. We will discuss now. So first of all, its unit is Pascal inverse. That means as volumetric strain has no unit, so volumetric strain by Pascal, that means pressure is below. So only if we will fix, or if we will consider this unit, the unit will be Pascal inverse. Okay. So compressibility unit is Pascal inverse. Okay. So let consider. So I am now explaining about compressibility. So for explanation, I am now to demonstrate one thing. So let's see, it is a container. Okay. For this in container, let's see, this is a boundary. This has a this thing is a boundary. Let's see, this thing is a boundary. Okay, this thing is a boundary. Okay. So if in this boundary there is some liquid in this, just in this boundary, up to this boundary there is some liquid, just assume. For example, for this liquid, pressure is 800 kilopascal, volume is 2 meter cube, and the density is 700 kg per meter cube. If I compress it and turn into or move into like this up to place, so liquid will be this, and obviously the pressure, volume and density will be changed. So it will change for this place, for this liquid it will change. P2 will be 2 megapascal, V2 will be 1.2 meter cube, and density will be 900 kg per meter cube. So for this thing, we can observe that as we compress it, the pressure will be increased, volume will be decreased, and density will be increased. Okay, so many changes are happening, but there is constant of mass. There is no escape of mass. Okay, so there is only thing, mass is constant. So by considering mass constant, or obviously mass constant, we have some calculate by mathematically. So how we are derive that, I am now explaining. Just listen. So only for this demonstration, only mass is constant. So if mass constant, mass we can write rho v. That means why rho v? That means rho is equal to mass per volume. So we can write mass is equal to rho into v. So rho v is equal to constant. If we add log both sides, it will be ln rho v is equal to ln constant. That means c, consider c. So ln rho v I can write ln rho plus ln v. It is a property of it is a property, okay, logarithm property. So ln rho plus ln v is equal to ln c. If we differentiate both sides this equation, so we will get d rho by rho plus dv by v is equal to 0. That means differentiating of any constant is 0. Okay, so if we look or observe that, we will get d rho by rho is equal to minus dv by v. So we can conclude that, which we are saying that volumetric strain we can also write in terms of density also. So in terms of density also we can write volumetric strain without using density option or density property. The only the volumetric strain is dv by v minus dv by v, as compressibility in this compressibility minus dv by v. Okay, so but in density, according to density, it will be d rho by rho, and we will get d rho by rho is equal to minus dv by v. So we can change or we can replace minus dv by v is equal to d rho by rho. So we can say that compressibility. Now I am just now considering talking about discussed about volumetric strain. Now whole compressibility I am discussing. So compressibility volumetric strain by volume change in pressure. So volumetric strain is minus dp by v. Now replacing density. So you will get d rho by rho dp, d rho divided by rho dp. So it will also an convert. So you can write that dB by VdP it is known as it is differential form, and beta is equal to Vf minus Vi. So Vf by Vi, so it is a negative term. Why it is negative? The discussion I am going, because dB, if you can say dB, so in this volume is decreasing, so it should be a negative, so that balance will be positive term will be both sides, both numerator and denominator should be there. But if you see denominator, that is positive sign, that means pressure change is positive but volume change is negative. So for balancing we have to add a minus, so that positive will be in a formula, will be considered as a positive term whole thing in a formula. So we are just adding some minus thing. Okay, so we can see write also d rho by rho dp. So df by d rho f by rho I divided by rho I rho into pf minus pi. Okay, positive. Okay, so if you consider two things, so change in volume by volume. Okay, so another thing, higher the value of beta means fluid is easy to compress. Higher the value of beta, that means fluid is easy to compress. It is very important. Higher the value of beta, that means change in volume is high, that means we are just easy to compress, just little bit compress, that means little bit energy or little bit power is required to just compress it. So for compressibility term, remember, higher the compressibility, the compression it is easy, that means easy to we can compress it. Okay, then okay, comparing air and water. So now we are already comparing. So if we compare air and water, beta air is greater, much more greater than beta water. It is obvious. Air is easy to compress when compared to water. When compared to water, air is easy to compress. That means beta of any air, the compressibility of air is greater than, much greater than compressibility of liquid. Now it is discussing about one term, incompressible. What is incompressible? That means we are not compressed. No, it is only theoretical. Actually, not exist as incompressible fluid in world. We treat fluid is incompressible only when beta is very small. Okay, so beta is very small. Just we are consider that it is incompressible. That means beta is zero. But there is no any fluid that is maybe zero. That means compressibility zero. That is no anything. But if it is small, that means 1, 2. There we can 1, 2 be very difficult. But if beta is less than which it's very small, beta is value is very small, we are considering it is incompressible, but actually there is no incompressible fluid. Okay, then we are go ahead for ideal gas. So what is ideal gas? Ideal gas, we are PV is equal to MRT, P is equal to absolute pressure, M is equal to mass, M is equal to mass, V is equal to volume, V is equal to volume, M is equal to mass, R is equal to characteristic gas constant, and T is equal to absolute temperature. Okay, PV is equal to MRT. We can write M either. So PV is equal to MRT. We can transfer this V to the denominator part of other side. So we can write P is equal to M by V RT. So M by V density RT also. Like that means rho RT we can write it. P is equal to rho RT. That's the main formula. Another same thing. We just modify by adding some properties. Okay. Another thing, PV is equal to NR mod T. That means nRT. That means N is a number of moles. That means N is considered number of moles. Mole concept is now introduced. So it is also, this formula is also written like moles concept also. This formula is written as a density concept also. This formula is, that means ideal gas ideal constant formula is also written in mole concept also. Okay, so PV is your nRT, N is your number of mole, R is your universal gas constant, and R bar is your universal gas constant, T is your Kelvin. Now, compressibility has two types. One is isothermal compressibility, another is adiabatic compressibility. Isothermal compressibility what? So beta isothermal is, we can write 1 by B dV by dP, which we already know the formula of it, which is where temperature is constant. Okay, is equal to, we can write 1 by rho into d rho by dP, where temperature is. That means isothermal means temperature is constant. That means temperature should be remain constant during compression. That means we are allowed to heat go. That means we are allowed to passing the heat. It is the main thing. So isothermal means temperature constant. If we are not allowed to go the heat outside, then temperature will be increased. So how it will be isothermal? So we have to be allow the heat to be passed. So we are temperature constant, and isothermal and temperature constant. Oh, adiabatic compressibility, and two types I already said. Compressibility is two types: isothermal compressibility, another is adiabatic compressibility. So in adiabatic compressibility, adiabatic is no heat transfer. There is no any type of heat transfer. Adiabatic means no heat transfer. That is isothermal means no temperature constant, but adiabatic adiabatic no heat transfer. That means what you can say? It temperature vary. That means temperature will be increased inside that. Okay. So find out isothermal and adiabatic compressibility of ideal gas. So if we will derive just I am reading that compressibility isothermal is 1 by rho d rho by dp constant temperature. So here we can add write one thing, that P is equal to rho RT from ideal gas equation. So if we derive that, we can write del P is equal to RT into del rho. As RT is constant, so constant will be side. So only derive what? Variable. So variable is d rho. So rho is variable. So if we add the differential concept, we will write del rho. That implies del rho by del P is equal to 1 by RT. Okay, del rho by del P is equal to 1 by RT. So del rho by del P at constant temperature is equal to 1 by RT. Here remember, yeah, we are proceeding. I will say then 1 by rho. I can write 1 by rho. That means for now I am discussing about derivation. So many derivation as many things will be happen. So just I am telling that. So now our equation we get that del rho by del P T is equal del rho by del P is equal to 1 by RT, where temperature constant. So if we multiply both sides 1 by rho, it will be 1 by rho 1 by rho 1 by RT. So beta isothermal, that means compressibility isothermal is 1 by P, where P is absolute pressure. As we are adding or we are discussing of ideal gas. So compressibility isothermal is 1 by P. It should be remembered. It is very, very important. Now for adiabatic process, PV to the power rho is constant. It is, remember, it is this equation comes from thermodynamics. When I discuss in thermodynamics, I will explain that time very large extent. So first for this time, please listen and see that for adiabatic process, P into V to the power gamma is equal to constant. So gamma is known as Cp by Cv, which is a ratio of specific heats. Specific heats is equal to ratio of specific heats is equal to Cp by Cv, which is lambda. Lambda is, remember, it is greater than 1. Okay. Then if I derive P into V to the power gamma is equal to ln C. So sorry, we are in adiabatic process what? P into V to the power gamma is constant. So if we add or we multiply both sides with ln, so ln PV add to the gamma is equal to ln C. So ln PV to the power gamma will be ln P plus ln V to the power gamma is equal to ln C. So ln P plus ln lambda gamma, that is not gamma, sorry, that is lambda. So lambda is equal, lambda into ln B is equal to ln C. So ln P plus lambda ln B is equal to ln C. The differential equation we will get del P by P is equal to so we will get dP by P is equal to lambda dP by B. So is equal to 0, as ln C is equal to, if we differentiate, it will be 0. So we can write del P by P is equal to minus lambda del B by B. So we can write a compressibility of adiabatic is equal to 1 by lambda P. Compressibility for isothermal is 1 by P only, but compressibility for adiabatic is 1 by lambda P. This will be remembered. And another thing, adiabatic compression is more difficult than, that means according to this theory or this observation, we are observed that adiabatic compression is more difficult than isothermal compression. Remember, adiabatic compression is more difficult than isothermal compression. With increase in pressure, compressibility decreases. Two things we have observed. Clearly observed that if that as another thing is add multiply in denominator, that means the denominator value will be if increase the formula will decrease. So formula decrease means we have to be more put power or put effort, full effort we should be give, more effort we should be give. So according to that, according to formula, we can observe that adiabatic compression is more difficult than isothermal compression. Okay. So with increase in pressure, remember, with increase in pressure, compressibility decreases. It is very, very important. Such, for example, this is a container we are compressing. For starting some time before starting or after starting some time, the compression is very easy. But at a one time it is that pressure which is very difficult to press that thing. That time compressibility decreases. That means we have to be give more effort to compress that thing. So as the pressure increases, large pressure increases, compressibility decreases. That means we are bound to give more pressure, so that means we have to be doing more effort so that we can compress. It is the main. Then we are now discussing about bulk modulus of elasticity. So bulk modulus is only the reverse of compressibility, 1 by beta. So we just rapidly I am going to finish. Minus V by dP by dV Pascal. Okay, so dP by d rho by rho. Okay, K is equal to rho by rho into dP by d rho. Okay, that is that in compressibility d rho by dP. Here rho into dP by d rho. Okay, where is differential from? And K you can write that minus VI BF minus PF minus PI divided by BF minus VI. So we can write rho I into PF minus PI divided by BF minus VI. For incompressible fluid, K is infinity. For incompressible fluid, for compressibility, that is K is equal to 0. Sorry, beta is equal to 0. For incompressible fluid, K is equal to infinity. So just opposite. 0 is opposite to infinity, opposite that thing. Okay. So higher the value of K, more difficult to compress will be. In this, higher the value of K, the higher the value of compressibility, that very easy to compress. It is totally opposite. Higher the value of K, it is more difficult to compress will be. Okay. That means it is bulk modulus of elasticity. Many will be forget that. I will forget to explain that, or I will forget to add that thing. The bulk modulus of K means bulk modulus of elasticity. Okay, it just reverse of compressibility. Okay, so bulk modulus of elasticity if higher, then the difficult will be compress. For compression, more difficult will be high. So according to this thing, so K water will be more difficult to compress than K, obviously. Just so like that, bulk modulus have two things: isothermal bulk modulus of elasticity, adiabatic bulk modulus of elasticity. Two things are there. So for isothermal bulk modulus of elasticity, the formula will be rho dP by d rho, where temperature constant. For adiabatic, rho dP by d rho, where adiabatic. Just think. Then isothermal means temperature constant, adiabatic no heat transfer. For the so that is thing. So if we compare bulk modulus of elasticity that means K between adiabatic and isothermal, we can observe that K adiabatic is more greater than K isothermal. That means adiabatic compressibility is difficult than isothermal compressibility. Okay, adiabatic compressibility is more difficult than isothermal compressibility. Okay, with increasing pressure, bulk modulus increases, but increase in pressure, what decreases? Compressibility decreases, but increase in pressure, bulk modulus increases. Just opposite. So, okay, bye. See you in next day. Have a good day.